Alright everybody, welcome to lesson 5 in our statistics playlist. This time we'll talk about all the applications of this normal distribution. So in our last video, if you remember, we learned how to use a couple features of our calculator to help us find either the shaded region underneath that bell curve or the specific z-score value that gave us a specific shaded region. And all of those were with regards to standard normal distributions, in the sense that everything we calculated was based on z-scores with an average of 0 and a standard deviation of 1. But you'll see for some of these, they aren't just standard normal distributions. They could just be any normal distribution with specific values for a mean and standard deviation. Now everything we're going to do remains the same. The context is just changed. So as a little bit of a recall, the area underneath that normal curve represents probability, so it must total to 1 or 100%. The shaded area underneath is the probability that a value is within that region if it's bound by the values A and B. So that black section shaded in on this curve represents the probability that a value is in that range. Okay. Now you can, like this says, we can extend this to include actual data values. We did this based on z-scores in the previous lesson, but this time we'll focus on, actual values. So example number 1 here, label on a box says it contains 200 needles. The manufacturer determines that the average number is 203 with a standard deviation of 5. Now assuming that this is distributed normally, what's the probability to the nearest hundredth a box will contain more than 200 needles? Okay, so I got some numbers. We can label them onto our curve. Now the average is 203, right? So I know my mean will go in the middle, right? There's the average, 203. Standard deviation is 5. Now assuming a normal distribution, what's the probability a box contains more than 200? Is what I'm looking for. So I know that 200 would be a value somewhere on the left side of, well, 203, right? It's smaller than it. Now I know that the standard deviation might tell me that this value is not 200, right? Like if the average is 203, one standard deviation to the left is 198, which I don't really need the standard deviation number. I really just need that specific data value point. Right? So 200 is the boundary point we care about, and I'm asked if a box will contain more than 200. So if I think about how that 200 really splits up this curve, well, if I have a value on the left of 200, I have a box that has less than 200 needles. But if I have a value at anything that's on the right of it, I've now got a box that has more than 200. So I'm really looking for the probability, in other words, the shaded region, that should show me a box that has more than 200 needles. So I've shaded the region that I want. Now it's a matter of going to find it. Now, in my calculator, what we would have done was normal, C, D, F. And again, I was asked for 4 specific numbers here: the lower boundary, the upper, the mean, and the standard deviation. Those are the 4 values that I need. Now, previous lessons, we did this based on, z-scores and a standard normal distribution, but this isn't a standard normal distribution. It is just some normal distribution, right, with specific context values, which is fine. I don't need z-scores to do this. I just need to make sure I have all the numbers in the right place here. So when we go to do this in our calculators, well, I need a lower boundary, and of the region I've shaded in, 200 is that lower boundary. Now the upper boundary, well, remembering this goes on forever to infinity, but it's to the right, so it's a positive value, right? 1 times 10 to the power of 99 is how we're going to represent infinity. The average is 203. The standard deviation is 5. So I've got all the things I need. I just have to go put them in my calculator. So second vars, a normal CDF is option 2. Numbers go in the same order. So 200, and then 1 times 10 to the power 99, 203, and 5. And when I hit enter, it will tell me a probability is, again, to the nearest hundredth, so 2 decimal places here. So my probability that I get a box with more than 200 needles is 0.73, or 73%. So any box chosen at random from this company, from this manufacturer, there's a 73% chance that it will have more than 200 needles. So it is the same, right? 27% chance, on the other hand, that you get a box that has less than 200. Okay, so exact same logic we talked about last time, but just specific values relating to a question. That really is all this is. Okay, we could also determine probability below a certain value. So the wording of the question will let you know whether or not which region you're shading, if it's above your value or below. Okay, so it does change from question to question. So this store determined the average wait time at an express checkout is 2.5 minutes with a standard deviation of 30 seconds. Assuming a normal distribution, what percentage to the nearest hundredth again of customers will wait less than 2 minutes? So if the average is 2.5, that average value is again the one that always is in the center. Now, assuming a normal distribution, what percentage wait less than 2 minutes? Okay, so if my standard deviation is 30 seconds, that's half a minute. So I'm looking at around 2 minutes, right? And I want to see where they wait less than 2 minutes. And the key word here is less, because that's going to tell me I'm shading the region that is below the value of 2. It just changes where my boundaries lie. Now 2 is going to represent my upper boundary, because again, this curve goes off to the left forever to negative infinity, which is the lower quantity. So lower and upper boundaries are decided on. Sorry, that's my ugly infinity symbol. Let me fix that. It's a little better. So same idea. Normal CDF. Lower boundary is negative infinity. Upper boundary is 2. Average is 2.5. Now the standard deviation, I can't use 30 because that's in terms of seconds. Right? I want everything in terms of minutes, so I should change that to 0.5, half a minute. Okay, so if I go plug all that stuff in, second bars, normal CDF, negative infinity, 2, 2.5, and 0.5. Enter. Okay, so a lot smaller than the last one. Nearest hundredth, 0.16, or 16%. Okay, so the picture's not really to scale at all, so don't really take that into account. It's just really showing us the region we care about. So 16% chance that somebody at the express checkout waits less than 2 minutes. Okay. So same logic as the other one. Find your boundaries and plug them all into your calculator to find that probability. It is that it's that nice to do this. Okay. Another type of question we could think about is, well, if I know where a certain range of values is going to lie, any values outside of that must be the alternate side of this probability. So it happens a lot with companies that need to manufacture parts, nuts, bolts, screws, whatever, to a certain specification in a certain tolerance. And if if they're outside of that range of acceptable values, we can't actually sell them, right, for safety purposes. So if this company produces cords that are normally distributed, again, you've got an average, length is 45.2, standard deviation of 1.3. In order to meet the guidelines, inspections are done, and only cords between 42 and 48 centimeters pass inspection. The rest are unable to be sold. Okay, they're rejected. If 20,000 cords are produced in total every day, how many would pass the inspection? So I can fill in some information into this bell curve, and I know that 45.2 is the average. And I know that I need a chord to be in between 42 and 48 centimeters, right? So here's my acceptable range. Any chords that are too long get tossed. Any chords that are too short also get tossed. Okay, so I need to find out the probability that a chord will fall into that range first. If I can do that, and I know that I'm making 20,000, well, I can adjust the probability from the total amount that's being made. So I gotta find the probability first. Okay. So let's go set this up first. So a normal CDF will get us our probability. So we need a lower boundary, which again, the lower boundary in that range there in blue is 42. Upper boundary is 48. Average is 45.2. And the standard deviation is 1.3. So I've got enough information to find the probability. Okay. So second bars, normal CDF. .2, and then our deviation is 1.3. So there's my probability. And we'll do nearest hundredth just for ease, so 0.98 or 98%. So most of them pass inspection, right? So it looks like we're within, 3 standard deviations of our average, which is good. Right? You don't really want this company to waste a lot of material. So this is a good number to have. Right? 98% of all the products they made we can keep. 2% get tossed. So that means I need to find out what 98% of the 20,000 chords that are being made happens to be. Because if I can do that, then I know how many chords we're actually keeping. So let's move that over. Okay. So if I do 0.98 multiplied by 20,000, which is 98% of 20,000. So that means we are keeping 19,600 chords. So we'll say they passed the inspection. Now, if I know that many chords passes inspections, I also now know how many get rejected, right? If I take the original 20,000 and I subtract 19,600, well, now I know that 400 get rejected. Okay, they fall outside the range of acceptable values. Okay, what action might the company take as a result? Well, they might, check out the equipment, because any chord that gets rejected as a company, that's lost revenue, right? Like you can't sell that object anymore, so now you're losing money. So they might check out the equipment, check out some of the other processes that happen in this plant. Who knows, right? But they're going to double check what they do to make sure that they don't waste any more product to waste the money. Okay, determining a length for a warranty. So there's a lot of different ways that the same question could get asked. So this music company determines the average life of their music devices. How old this question is. It's 32.4 months, so just under, 3 years or so, with a standard deviation of 6.3 months. What length of warranty should be offered if they want to restrict repairs to less than 2%? Right, less than 2% of all devices sold. So this time, since I have a percentage, that's my probability. In other words, that's the area. So we got to think about this one a little bit backwards than all the other ones we've done. So we'll still add in some numbers here. Right, I know the average is 32.4. I know the deviation is 6.3. So what length of warranty should be offered if they want to restrict repairs to less than 2%? So if I think about what this area is really going to represent, I want that to be as small as possible, right? Less than means I have to be smaller than that 2%. So if I think about where this area is really going to be, right, it's really, really small. I don't want to replace devices, within a month, because then my product isn't great, right? There's something wrong with it. So this shaded area is my 2%. In other words, as a decimal, it's 0.02. But I don't know how many months I want that to be, right? If I want to restrict repairs to less than 2%, I have to find out what this Z-score is. Well, sorry, I shouldn't say it's a Z-score. Let's call it just X, right? The specific month, since this isn't a standard normal distribution, I shouldn't use that score. So let's call it X. We're looking for the specific amount of months where I want this to happen. Okay, so if I think about how we did this before, this is the other case in my calculator where I can use inverse normal. Right? I know the area that's to the left of my boundary point. So the area to the left. And then we still need the average and we still need the deviation. So if I fill in what I know, area to the left is my 0.02. The average is 32.4. The deviation is 6.3. So I got my calculator, second bars, option 3. If I throw in all those numbers, 0.02 is the area to the left, 32.4 is the average, and 6.3 the deviation, and it will tell me in a number of months that specific one, and I guess we'll go nearest 10th, 19.5 months. So if I restrict this, right, what length of warranty should we offer? Well, I can't really offer half a month warranty, and if I round this up to 20, then I'm going to be giving repairs to more than 2%, only slightly. So I'm going to round down in this case and offer a 19-month warranty. And if I offer a 19-month warranty, that means I will only be repairing less than 2% of the devices. It'll count within the area. If I were to round this up to 20 months, well, then I'm going to have this X value shifted over just slightly, and it would be more than 2%. Okay, so a little bit of a context thing to think about with regards to rounding here. Let me see what's left. Just a couple more that are all very, very similar. Okay, determine the distance driven. So this is the same idea, again with a warranty, just in terms of a car instead. Okay, so this car manufacturer determines their transmission has an average life of 80,000 kilometers. So there's my average number, 80,000 in the middle. Standard deviation is 10,000. They don't want to replace more than 3% of transmissions. How many kilometers should they guarantee it for? Essentially asking you, what should the warranty be? So again, that percentage, as soon as you see it, that's your probability or area. So 3% is very, very tiny. 0.03, or in other words, that's 3%. Okay, and I'm looking for the X value here, the specific number of kilometers that I should guarantee for me to replace less than, they don't want to replace more than 3%, so they want to replace less than 3%. Round to the nearest whole number. So same idea, inverse normal. For the area left, this time is 3%. Average of 80,000. 10,000 for my standard deviation. Okay, So we'll go find the data value for x that makes this work. 0.03, then 80K, then 10,000. There we go. So to the nearest whole number, 61,192 kilometers. Okay, and again, we've already rounded down here, so that will take care of the rounding scenario, because I don't really want to round up to the next kilometer. That'll be too much that I'm repairing. So this should be the length of your warranty, or what you should guarantee. They should guarantee 61,192 kilometers. Right? Any more than that, and they're going to repair more than 3%. So this is the number that you need, that boundary point, to give you that shaded region of 3%. Okay, so very, very similar. Okay, example 6, again, really no different. This kind of just puts a lot of them together. So the life of a particular engine, normally distributed, average is 8 years, and the standard deviation of 2. So what's the probability that an engine lasts between 7 and 10 years? So 8's in the middle, 7 should be somewhere to the left of it, 10 somewhere to the right. Okay, so there we go. Now if I'm looking for the region in the middle, that's a normal CDF question. All right, I'm looking for the probability. So lower boundary is 7, upper is 10, mean is 8, standard deviation is 2. Okay, so probability equals nearest 10,000, so I know this is going to be a decimal. And it should be if it's asking me for probability. So second vars, normal CDF is 2, so 7, 10, 8, and 2. Okay, there it is. So 0.5328. Okay, which is pretty good. It makes sense that an engine that you choose, right, a particular lawnmower, there's about a 50% chance it'll last between 7 and 10 years. Okay, what percent will last more than 12? So again, 8's in the middle. 12 is greater than it. Percentage that'll be more than 12, so here's my shaded region this time. So again, it's still the same type of question, still a normal CDF. But now the boundaries are different, right? This isn't going to positive infinity, so my lower boundary is 12. Upper is my infinity number. Average of 8, deviation of 2 still. So probability equals normal CDF one more time. So there's 12, and then infinity, 8 and 2. Enter. So really, really small this time. 228. Okay, which makes sense because it's not very likely that a lawnmower will last more than 12 years. So it's a really, really small percentage. Okay, only about 2%. Oh, I missed a 0, I think, somewhere. 0.022. I guess that would be 23 now. Okay. So that's better, right? About 2.3% will last that long. Okay, the company guarantees these engines will last at least 6 years. Okay, so at least 6 years. Now, if 10,000 engines are made, how many should they expect to replace under this guarantee? Okay, so this is a pretty generous, guarantee, because if the average is 8 years and they guarantee it for 6, well, you can pretty much replace your lawnmower and they'll cover it once you hit that 6-year mark. So if you've got it for 6 years, basically take it back to the company, they'll give you a new one. So they're going to expect to replace a lot of them, I would imagine, because you're going to replace it if it's 5 years, 4 years, 3, 2, or 1, right? You're going to replace any number less than 6. So we need to find out the probability that a lawnmower gets replaced, and then find out how many that translates to if 10,000 are made. Okay, so normal CDF one more time. Lower is that negative infinity because it goes on to the left forever. Upper boundary is 6, average of 8, deviation of 2. Okay, so one more time. Throw all these numbers in. Okay, so there we go. Okay, so the probability that a lawnmower lasts less than 6 years is about 16%. So 0.1587. Now, since 10,000 of them are made, if I find out what 15.87% of 10,000 is, I'll multiply them. I know that they are going to replace 15, that was a silly calculation. How do I write this? Replaced. Right, so they're going to replace 1,587 of them because they are going to last less than that 6-year mark, which seems like a lot that they're going to lose money on. What guarantee should they offer then? Because 6 seems like they're replacing too many, right? Like almost half of the lawnmowers they're creating, they're just going to give away for free, essentially. What guarantee in years should they offer so that less than 3.5 produced are returned? So 3.5 is a lot smaller than 15%, so I should be shading a lot less of this curve. All right, so here's my area this time. 3.5% or 0.035 as a probability, right? A lot smaller. I don't know the specific value here, but I know the average is 8 years. Okay, so this again, an inverse normal scenario where the area to the left is 0.035, average of 8, deviation of 2. That still hasn't changed. So number 3 this time, so 0.035, 8, and 2. There is a much better guarantee for them. So what guarantee in years? So I do have to round this down to the nearest whole year. And again, don't take this bell curve as being to scale, but 4 years is what the guarantee should be for less than 3.5%. Okay, so they should do a 4-year guarantee. Okay, so all of the things we've talked about in the last, 2-3 videos come together in this one, where we can again use our calculator to calculate a lot of these things to determine if a warranty is good or not, and finding specific probabilities for some products. So there's one last lesson in this where we'll talk about margin of error, things like that. Again, you've got a summary here and some practice down below if you want to try it. So last video linked up above, and we'll see you next time.